Now let's see that you've done the analysis and you got your demand MU, okay, and from a structure analysis, let's see how to calculate your amount of resistance. So we have done this, and then we got R in terms of this. So R, the moment resistance, can be expressed as a function of the amount of reinforcement PT that we are providing on the tension side. So that we have seen that. So this is one directly. Or usually what will happen is the moment from analysis is given to you. For that, you have to design the amount of reinforcement. So PT can be solved. This is a for under info sections. PT can be expressed as a quadratic equation, and for a given mu by bd square, we can calculate directly solve this PT amount. Okay, so there are two ways of calculating the amount of tension steel that is required once the demand is given to you. Okay, so let's say method one, which is your first method. One way of doing it is first you calculate the neutral axis depth for the amount of steel that is required from the moment demand, from neutral axis from the moment demand. Then using that you calculate what is AST. So let's see. From moment resistance, we know either if I am taking moment about concrete, then it will be TS multiplied by D minus 0.4 XC, which is your lever arm. Similarly, same thing, moment resistance also can come in terms of uh, concrete also. Okay, so if I take from concrete, it is going to be 0.36 FCK BXU multiplied by D minus 0.4. So this is the moment resistance. Both of them has to be same, right? Now let's say that if I am looking at moment resistance only from tension side, by taking the tension force, it is going to be this. Okay. Now AST is what I'm interested in calculating. So how can we express AST? AST can be expressed as in terms of moment demand divided by this 0.87 Fi, and if I take the D out, D out, then it is going to be 1 minus 0.42 XC by D. Now, for a particular government, for example, let's say I'm giving a 600 kilonewton meter, okay, and I want to calculate what is the amount of steel that is required. Once I fix my breadth and depth, then if I plug it in this equation, of course, depth, effective depth will be, I will fix it, and yield strength, I will be fixing it. Now, only thing I don't know is what is this XU by D that I have to use in your calculations to find out what is the AST required. Now, how do we get this AST? So basically, we can solve this again from, let's say, from if I'm taking moment about concrete force, you can moment resistance again, you can express in this way. Then in this equation, let's say that I'm let's say I'm dividing, let's say, by uh, d square, for example, let's say, or in other words, maybe by uh, so let's say this A multiplied by d by d. Okay. So what will happen? So this 1d we can 0.36. This of course FCK. So XU by d it will come 0.36 XU by d. Then again one more d, if I take it out, it is going to be 1 minus 0.42 XU by d. Then you will have two d's, so it will become d square. Okay, so you'll have, because when I multiply and divide by d, I'm not changing anything, right? So if I take this d also out, it's going to be 1 minus 0.42 xu. So you see here, this d and multiplied by d will get d square, then this d will become part of xu by d. So I can simplify mu in terms of this xu by d like this. Okay, so you see here, when I try to take this xu by d, this forms a quadratic equation. So for a particular amount of moment demand, I can solve for this xu by d in a quadratic equation, where the solution for xu by d can be expressed in terms of this equation, which is one of the solutions, where R is mu by bd square. So in other words, for a particular moment demand that is given to you, you first calculate R value and plug into this equation and find xu by d. Then once you get your xu by d, then you go ahead and put in this equation to get your amount of steel that is required. So what are the steps involved in this approach? First you calculate this. This is your first step. Then you calculate this is your second step. Once XU by D is known, then you put it in this, then you get your, this is your third step. This is your amount of steel. So this is one way. Again, all of these, assuming that the steel is going to yield, right? And you have to make sure that the XU, whatever you're calculating, should be less than your XU max. Okay, this is your first approach. The second approach is what we have done previously, where we expressed mu and pt as a quadratic equation, right? Again, if you look at it, r, which is your input from your structure analysis, moment is given to you. Once your breadth and depth is chosen, so you can calculate this r value. That we have expressed this equation in terms of pt. Again, what is pt? Again, go back. It is going to be 100 AST by BD. It is the percentage of steel. Okay. So the moment resistance when steel is yielding can be expressed as a function of your amount of steel on the tension side. It is a quadratic equation. So again, we can solve for this PT for a particular value of R. So in this approach, it's a more direct approach. Okay. So you directly calculate your R value and plug in this equation to get your PT. That's it. So it's a very simple and straightforward approach. The previous approach was first you calculate R value, then you get your XU by D value, then you put it in your AST equation, get your AST. Here it is a more direct approach. They're all the same way only, but the first approach had three steps. Here it is directly you can get your. But here also what we have to make sure the PT that what we are getting should be less than PT limiting. Okay. So why is this condition? We always want steel in tension to be yielding. Okay. Or in other words, epsilon S T tension steel has to be greater than 0.002 plus 0.87 Fy by ES as per your IS code. So this condition has to be satisfied. Okay. So then only we can express all these things in terms of quadratic equation, because then only your stress will become constant value of 0.87 Fy. Otherwise, we cannot solve directly form this quadratic equation. So for over-reinforced section, if you are designing it, capacity calculations, you have to use strain compatibility approach and do it in an iterative way. So this kind of simple quadratic equation can be derived only if your amount of steel is less than AST limit, or PT is less than PT limit, or when XU is less than XU max. So please keep that in mind. Okay. Right. So this is what it is given in your SP 16 table also. Okay. Mu by BD square, and different tables are given as a value for your grade of, depending upon your grade of steel. Again, we can also use SP16 and find out for a particular amount of demand what is the amount of steel that is required. That is given in the form of tables for different grades of steel. Right. Okay. Okay, we will now quickly show the two methods that we have discussed, how to calculate the amount of steel that is required for a single reinforced section. Okay, so this is one example problem, single reinforced section. Let's say I've just chosen the dimensions 400 and 600 mm, okay, and similar to what we have done in the previous examples. And even to get your demand, you have to assume some dimensions for structural analysis, right? So we have done that. We have assumed these dimensions. For the loading requirements, it works out to be the moment demand is 500 kilonewton meter. Let's say that I'm taking a characteristic strength of concrete of 40 megapascal and grade of steel is 500 megapascal, and this beam is exposed to moderate condition. And what is required is we need to calculate the amount of steel that is required in tension to for a moment demand mu equal to 500 kilonewton meter. So that is what we are looking at. Okay. And the information that is given to you, you have 20 mm longitudinal bars are available, and stirrups are going to be 10 mm bars. Usually stirrups are you want to bend it in the side, so 8 mm or 10 mm is required. If you have a very heavy requirement and to increase the spacing, sometimes we go 12 mm, but not more than 12 mm. 10 mm and 8 mm are preferred stirrup diameter bars. Right, let's see. So we looked at two methods, right? The first method, let's look at now. Say, for example, for a nominal cover as per IS 456-2000, so we need to have a nominal cover of 30 mm, okay, for a moderate exposure condition. So the effective cover is always measured from the outside surface to the this is your effective cover. Let's see how to get the effective cover. Effective cover should be the clear nominal cover, which is 30 mm for the exposure condition that is specified, and then 10 mm, which is your stirrup, okay, stirrup diameter. The stirrup will come outside this, okay, we are not represented here. Then you have half the diameter of the longitudinal bar. I am assuming 20 mm bars will be will be used. Okay, so this is an assumption that we are making. Okay, so that is why half the diameter. So basically here you are going to have some stirrups as well. Okay, so clear cover plus the stirrup diameter plus half of that, so it works out to be 50 mm is your effective cover. Okay, right, so this is stirrup, this is half of the diameter of the longitudinal. So what is the effective depth that is left? The total depth minus the effective cover to the tension most reinforcement longitudinal bar is your effective cover. That works out to be 550 mm. Right. So now check for single intersection whether for that particular how do we say, we have to design the amount of steel for 500 kilometer meter. Now we know that once the grade of steel is fixed, we can calculate your limiting moment of resistance. Okay, so that is purely function of your Xc max and by D and Fck. So we have derived this equation, right? So if you plug in your Xc max by D, for example, for Fe 500, Xc max by D is, you know that value, Xc max by D is 0.456. Okay, so that's what we have calculated. So if you plug in that value, FCK is given to you as 40 megapascal. So you can substitute, and then you substitute for 0.456, and then you know this is what we got. Okay, you remember this is purely based on your strain condition 0.0035 and strain with the steel of 0.002 plus 0.87 Fy by S, Fy by Es, right? So if you do that, then you get your Xc max by D for a particular grade of steel, right? So if you plug in these values and you get a value of 646 kilonewton meter is the maximum moment resistance this section can offer, which is greater than the moment demand of 500 kilonewton meter. So the section can be designed as a single reinforced section. Now, if this moment demand, let's say 700 kilonewton meter, then it will become higher than your limiting moment of resistance. Then we cannot design this section as a singly reinforced section. In this case, my moment demand is actually 500 kilonewton meter, so which is okay. So we are not exceeding the limiting moment of resistance. Now, why is that again condition put? We want to make sure that the steel is going to yield before concrete reaches a compressive fiber strain of 0.0035. So, you know, that is why the code is limiting what is the maximum moment of capacity particular section can have. Okay. Now we have checked this. Now our idea is to calculate what is the moment, what is the area of steel that is required for moment demand of 500. Now let us see what we are getting. The first method, okay, the first method we discussed. There are three things. First is we calculate your R value. Okay, R is nothing but your mu by BD square. Let's say what is that we get. Okay, so you get 500. Everything you keep it unit consistent. 500 into 10 to the power 6, and B is 400. Effective depth is 550. When you do that, you get a value of 4.13. It as an unit. Okay, so it's not because you have kilonewton meter and BD cube, which is unit of meter cube. So basically, you'll have kilonewton per meter square or Newton per mm square will be the unit for your R. Now what we have done, I have to calculate, second step is to calculate your Hc by D. That can be found out using your quadratic solution of a quadratic equation, right? So if you plug in for your R and FCK, then you will be able to get your Xc by D. So that's what we derived in the previous part of the module. So you can go back and check the video and we can get your XU by D. So for this particular scenario, we got a value of XU by D equal to 0.336. Once I get my XU by D, then I can get my moment of resistance or AST directly as from this equation from the moment resistance. Now Fy is known, D is known, moment is given, input value 500 km and then XU by D is, we have calculated that as 0.336. If you plug in all this value, you get a value of AST equal to 2425 mm square. So, that is the amount of steel that is required for moment resistance of 500 kilonewton meter. So, this is first method. Now let us look at the second method. Second method is a more direct method, right? So we can directly calculate your PT as a function of your moment demand, or in other words, as a function of your R. So let's see how we do. So this is a method. So we got your uh, uh, moment mu by BD square as 4.13. Then a PT expression was given to you that was derived. Again, you can look at the previous part of the video. If you substitute R in this equation here and FCK is given to you and FO is known to you, so you can directly find your PT for the particular moment demand. So if you substitute that, you get a PT by 100 of 0.0110. If you multiply by 100, you get a reinforcement PT of 1.1 percentage. If I multiply this by 100. So 1 percentage is the amount of steel that is required to reach this moment demand of 500 kilometer meter. So again from PT you can calculate what is the AST required. It will work out to be exactly same thing that we have done in your first method. Okay, so this is the way that we can do. But again, in all these things, this quadratic equation can be developed only for sections which are under reinforced. So we have to make sure that the moment demand is less than the limiting moment resistance for each section. So that limiting moment resistance again already we have expressed in terms of your Xu max by D. So you can quickly check your limiting moment resistance. If your moment demand is less than your limiting moment resistance, you can design as a singly reinforced section and directly you can calculate your area of steel as a function of your moment demand, which is your R value, which is mu by PD square, right? Both approaches you can use it to quickly calculate your amount of your steel. Again, in all of them, we are making sure that the steel is going to exceed its yield strength. Again, what is your yield strength is very, very important, which is 0.002 plus 0.87 Fy by ES. So for Fe 400, Fe 500 steel, it's going to be 0.00407. So you can go back and do your strain compatibility analysis. Also, you will find that this value will be greater than 0.00407. Okay, so that is your yield. Okay, this is what I. So this way we can find out. Okay, right. Now let us see what is the value that we are getting with your moment curvature analysis that what we have done, right? So if you go back to the previous parts of the module, we took this example of a very small amount of steel of 1200 mm square, right? Which works out to be, if I divide that by gross area, it works out to be about half a percentage of steel, PT of about half a percentage. Here in IS code calculation, PT is defined in terms of B in effective depth, not your overall depth. That difference you should keep in mind. Okay. So here you can take, I am taking a 500 megapascal steel again, characteristic compressive strength of 40 megapascal. Now let us see. We have calculated. Now what I am doing is not just the AST for this particular problem, not the demand. So this is now AST is different. For this top amount of steel, I am calculating what is the neutral axis depth and what is the moment resistance and so on as per your IS code version, because this is the problem that we did in your previous module. So go back and look at your module 5.1. Okay, so that is the same example that we did. Okay, so if you go back, as per IS code, the tension force is 0.87 Fy times AS. So it works out to be 522 kilonewton. and neutral axis depth is, we are equating, this should be equal to your CC, and CC we know that it is equal to 0.36 FCK B times XU. So you substitute that, you get XU equal to 90.63 millimeter, right? Then once XU is known, moment resistance, I can take moment resistance about the compression force. Okay, so I'm taking moment about this point. Okay, so I'm going to do this. The lever arm is basically, you know, the lever arm, that's going to be your D minus 0.42 XU. So this is your lever arm. XU is already known, D is known, tension force is known. So you can calculate your moment resistance as 267.2 kilonewton. Okay, this is the same cross section that we did in the previous module. Okay, so you can see that the moment resistance 267.2 kilonewton. Now what is curvature at failure? Curvature is failure is the slope. Okay, so the slope can be calculated from top compressive fiber strength divided by the neutral axis depth. Okay, sorry, this should be 90.63. Okay, so if you do that, then you get a value of 38.63 into 10 to the power of minus 6 per millimeter. Right? Now, I want to compare this with what you got from your actual values that we did your detailed moment curvature analysis. So, only thing is the stress strain curves were different, right? So, we took F prime C equal to 40 megapascal. So, if I cylinder strength is 40, what would be my cube strength? 40 multiplied by 1.25 megapascal. So, it works out to be 50 for cube strength. Now for this cube strength, what is characteristic strength? 50 minus 1.65 times 5, that works out to be about 42 point something. Okay, 3 or something, 42 point something megapascal. Okay, so you can look at the number. So 50 minus 1.65 times 5, it could be 41.7. In fact, this is 41.7. So that is the reason I am taking, okay, so for 40 and 40 nearly same. So that is the reason here I am taking cylinder strength of 40 megapascal, which will be closer to the characteristic strength of 40 megapascal that we have considered in the previous calculations. Okay, so they will be nearly same. There's slight difference just to show you how much is the conservatism. Okay, for under reinforced section, anyway, we have seen that concrete strength will not play a major part, right? So if I substitute these values, then you will find that for actual material properties, this we have already done. Moment resistance was 316.1 kilonewton meter. Curvature at failure was 68.1 into 10 to the power of minus 6 per millimeter. Okay, so please refer to this example. I'm not redoing this calculation. We have already done that in your part 1 of the module in example 5.1. Okay, so if you go back and if you compare this, okay, so we get, when we use actual material property, the mean cylinder strength and your parabolic model, you get a moment resistance of 316.1 and you are predicting the curvature at failure of 68.1. As per the IS code method, it is not too bad. If you look at it, it is 267.2 for the same section, same reinforcement. Instead of actual material properties that what I am getting it in the lab and perfectly elastic plastic, I am using now code specified design stress strain curve. So if I do that calculation, IS code method is giving a value of 262.2 kilonewton meter. So if I take the ratio 316 divided by 267, so roughly if I take inverse of this, your IS code is about 85 percentage of your actual value. So that means the IS code is predicting the capacities at about 85 percentage of that your actual value. So it's not too bad because it's an under reinforced section. It's going to give you a lot of warning. So the code predictions are conservative, but it's not very conservative also, right? And however, if you look at your curvature at failure, the IS code method gives you that curvature as per the failure condition of IS code provision is going to be 38.6, which is again lesser than what you are going to get when you are using your actual material properties. Again, in the actual material properties, stress strain curve for steel, we have taken bilinear curve. You can plug in the other forms also and you can calculate the variations. Then the capacities may slightly be different. Okay. So this I just wanted to tell you that the IS code provisions for Flexure is conservative, but it's not quite that drastically very conservative, and it is reasonably able to predict the capacities with a good accuracy. So that is a point what I wanted to